Good evening, students. I welcome you for another amazing session. A very important topic today, crystal field theory student. Students, last time we have discussed valence bond theory and it was proposed because it was required in order to predict the magnetic properties of the coordination compounds. As Werner did not give any idea about the shapes and geometries of the orbitals and also the paramagnetic or diamagnetic behavior of the coordination compounds. The
Yes, sir.
basis of valence bond theory. Can you tell me in 1 minute, student, what is the basis of valence bond theory? Question is given in the paper. What is valence bond theory? What will you write, students? You have to give your answer. What is the basis of valence bond theory, students? On what basis you gave the valence bond theory, students? Okay. We are always beginning with question answer sessions because we have to create energy, students, and you have to keep thinking. That question is given. What is valence bond theory, student? What is your answer? Give me fast, students.
Uh, so the valence bond theory is based on the fact that central metal atom or ion have vacant d orbitals like n-1 d, ns2 and np orbitals, and also nd, ns2 and np orbitals which it uses for bonding. Ligands can donate electron pairs. Then these orbitals under the influence of ligands mix up and form hybrid empty orbitals which are more stable.
Okay, I would say okay. The answer is okay. Basically, what we are trying to say, students, let us make the things very short in papers in exam. That this involves the formation of a bond between bond between the ligand and the central metal atom ion. The central atom ions orbitals hybridize. Which orbitals hybridize? You have said what orbitals it has, students. It has n minus 1
N
d,
minus 1d,
ns, np,
ns2.
and nd orbitals.
Yes,
They
sir.
can hybridize to get empty vacant orbitals, and then the ligands have lone pair of electrons. They can donate in the empty hybrid orbitals of the central metal atom ion, and this is a formation of a coordinate covalent bond where ligands are donating their uh, lone pairs of electrons in the empty hybrid orbitals. So that involved what we said, hybridization of the orbitals, basically. So metal atom under the influence of ligands can hybridize the orbitals. Which orbitals you are saying? N minus 1 d
D, ns, np and nd.
and p. And these vacant hybrid orbitals can accept lone pair of electron, students, from the ligands. Therefore, the bonds are formed, and that could explain the hybridization. And on that basis, you could predict the directional or the geometry of these coordination compounds. But the thing was that when we try to predict the magnetic behavior, what we said that certain ligands, sometimes we said there is a pairing up of the electrons, so it becomes diamagnetic, and sometimes we are saying the electrons are not paired up. So there is some doubt in that because we have not been able to clearly define which ligands will be able to pair up and which ligands will not be able to pair up. Because we only said, as you have seen in a list, ammonia and water were appearing in weak as well as strong ligands. I mean, actually the valence bond theory has given no idea about the power of the ligands. It has not defined anything like strong ligand or weak ligand. And we are ourselves saying, okay, this ligand is coming, so it is diamagnetic, therefore electrons get paired up, and the vacant orbitals can be used on the basis of hybridization. So it is not that clear actually. There is some doubt in the terms of the paramagnetism or diamagnetism in the valence bond theory. So therefore we can say that
Okay.
it has made an attempt to explain, students, It has made an attempt to explain, we are saying, the magnetic character using hybridization, and we said ki, okay, these ligands are coming, so there is a pairing of the electron. In some cases we said pairing doesn't take, and on that basis you are calculating the magnetic behavior. But this is actually what we are saying, there are limitations of the valence bond theory, there are drawbacks or limitation. Every theory has some problem, students, some drawbacks. So that is why we go to the next theory. And valence bond theory is not giving any information about the color of the magnetic coordination compounds. It has not defined anything why they are colored. Does it give any explanation for that, students? Does
No.
it explain the color of the coordination compound? No. Therefore you can say that the VBT is based on certain assumptions. What assumptions you made, students, in VBT? We are saying certain ligands, when they form the compounds, pairing of the electrons took place. In some cases, we said that pairing is not taking place. So on that basis, we said that this is a hybridization, because experimental result is like this, that this compound is paramagnetic. Therefore, we predicted the hybridization based on that. So it is based on certain assumptions which we do not know how much good or bad they are. Okay?
Okay.
And it also it is not giving any quantitative relationship of the magnetic data. No quantitative, no quantitative, student, interpretation is there. Interpretation of the magnetic data. Magnetic data, how we get from experiments. And it does not explain the color, student. Here I have written, it does not explain the color exhibited by coordination compounds. It does not give quantitative interpretation of thermodynamic and kinetic stability of the coordination compounds. It does not make exact prediction regarding tetrahedral and square planar four coordinate complexes. When the coordination number is 4, sometimes we are saying the hybridization is sp3 tetrahedral, sometimes we are saying square planar, but it is not very clear on what basis. It is not distinguishing between weak and strong ligands. You told me last time that ammonia and water has been placed in the list of strong and weak. Told
Yes,
me?
sir. Yes, sir.
So actually, certain compounds in certain compound they were behaving like this. That in the on the basis of valence bond theory, valence bond theory has not given any thing about weak or strong ligands, because there is no field in which this is talking. It is only saying that the ligands have lone pair of electrons and metals have empty hybrid orbitals. So they donate it to the empty hybrid orbitals. Bonding takes place. That's all it said.
Okay. Yes, sir.
Does it talk of any magnetic field or any field or any electric field is being created by any ligand or around the metal ion? It has not talked about any field of the ligand, students. So some confusion discrepancies are there. In
Okay.
order to overcome these difficulties, students, these drawbacks, we go to the next theory. That will be very important because it will be 100% asked. There will be a question from valence bond theory also. Now another question will come from student crystal field theory, what we call as CFT.
Yes.
So student, let us see what is crystal field theory. I am happy that you interact with me. You are answering questions, students. My purpose is that you should become so good that you will be able to answer questions in paper in a very short period of time. The problem is comes with the students that they know the answer, but they don't know what to write, how to write. Sometimes, student, if the question is not objective type, how many lines we are writing without any reason. So we have to write less and to the point, correct information. Don't write any information which is not required or which is vague, or I mean, sometimes we write more than the right becomes the wrong. Got my point?
Okay. Yes, sir.
So what happened in valence bond theory, students? You are saying the hybrid orbitals, vacant hybrid orbitals of the metal ion, they were available and the electrons went to from the ligands to the vacant
Vacant
hybrid
hybrid
orbitals.
orbitals.
Why did they hybrid? When the ligands approach them, they got hybridized. ठीक है? So
Yes,
that
sir.
is okay. So so far there is a difficulty and there are limitations of the students. So what we are now talking? What we are talking? Crystal field theory. There is a crystal student, and I'm saying there is a field student. Now I'm talking of field because up to now they never said weak field or strong field. That definition has not been given by Valence Bond. We have told you the limitation. There is no
Yes,
field.
sir.
So what do you mean by strong field or long field? ठीक है? So what is student? What we are saying? Crystal field theory student. This is a purely electrostatic model. Purely electrostatic model student. What it means? What do you mean by electrostatic model? That means it is purely ionic. What we are saying that there is a electrostatic interaction means what? What do you mean by electrostatic interaction? What do you mean by
Involving ions or charges.
electrostatic? Electrostatic interaction is where there are ions student. There are ions. That means there is a metal ion student and there are ligands students. And what we are saying, the interaction between them are purely electrostatic. That means student legals and these metal ions are treated as charges student, as charges. Ligands, you are saying they are acting as point charges students, point charges. And ligand is also acting as a charge. It has a positive charge. You are saying ligand is having positive charge, M3 plus, M2 plus. So there is a positive charge on the ligand, on the metal ion, and there is a negative charge on the ligands. Negatively charged, if the ligands are negatively charged, there is no problem. If I say negatively charged ligands, negatively charged ligand, you already know they have negative charge. If I say Cl minus student, there is a negative charge on them, which is clear. So they can act as point charges, point negative charges, point negative charges. If there is a negative charge, there is a field around them, field around them. And metal ion, you are saying you have metal ion Mn plus. So there is a positive field around it, positive charge around the metal ion. Positive and negative, what they will do? There will be attractive force between the two. So just like NaCl, you are saying sodium positive and chloride minus. There is an electrostatic force. There is an ionic bond between the two students. There is no covalent bonding. There is no covalent bond. That was a coordinate covalent bond when the lone pair of electrons is donated to the empty hybrid orbitals, I'm
Hybrid
saying, hybrid
orbitals.
orbitals of the metal ion. So here there is a purely electrostatic. Ligands are treated at point charges in case of the anions. If there is a neutral molecules are not carrying any charge, but neutral molecules, students, they have dipoles. What they have, student, neutral molecules. If I write H2O student, this is negative, this is positive, and you know there is a dipole. If I write ammonia student, then you know what it means, because these are having electronegativity difference. So what you know already, there is a dipole student. So in neutral molecules also there are dipole student, so we can treat them as charges. But we are seeing dipoles. So anions are negatively charged, neutral molecules are dipoles. And we are saying this crystal theory was proposed by a physicist. He is a physicist, not a chemistry man. See, a lot of work is done by physics people because electrostatic model is a physics model where they are talking of charges. To describe the bonding in coordination complexes, to rationalize, predict some important property of coordination complexes. Actually, the complexes are highly colored students, and there is a magnetic properties. In order to explain their magnetic properties, in order to explain their color, in order to explain their spectra, we take spectral properties also, which we'll study in higher classes. So this model was proposed by a physicist student. It is a based on purely interaction between the ligands and the metal, treating them as charges. So we are saying students, the electrostatic interaction between metal ion and ligands. The ligand is anion metal and atom is cation. This is my cation, ठीक है?
Yes, sir.
And these ligands are my anions students. So they are oppositely charged. They are oppositely charged. If the ligand is a neutral molecule, the negative end of the dipole is attractive. There is a negative end of the dipole. Negative end of dipole.
Dipole.
So this will be attracted toward the positive charge metal ion. So it treats the ligand is a point of negative charge. Ligand is a negative charge, point charge students. What it means, student? The metal has got which orbitals? Tell me. Which orbitals are taking part in the transition elements? Which metals are involved, student? If
D
I
orbital.
take 3D series, you have 3D orbitals.
Yes,
So
sir.
the d orbitals are involved. Or you are saying this metal, student, every metal you will write. We will take any example, titanium or anything. It has got 3D orbitals,
Yes, sir.
and 3D orbitals, metal is positively charged, but there are electrons in the 3D orbital, students.
Yes, sir.
And now the negative charge is coming. Negative charge is approaching the metal. How they, you have seen in the coordination compounds, there is an octahedral shape, tetrahedral, square planar. So the ligands are approaching the metal ion. Before the ligands are approaching, student, there are 5d orbitals. How many? 5d orbitals. And as we say, these 5d orbitals, students, how many d orbitals are there? 5d orbitals. They are degenerate, student. What do you mean by degenerate? They are all of the equal energy. They are symmetric, students. What do you mean by symmetric? That there, if there are electrons in the d orbital, there is a field around them. There is a electrostatic field. This field is symmetric, students, because there are electrons in them. This field is symmetric. And what will happen? The ligands which are negatively charged, they are being attracted by the positive metal ion. Positive metal ion. The ligands will approach the metal ion. Okay? We are not saying they are forming bond now. I'm not saying they are forming bond. I'm saying there is a field. There is a field of the ligands also, students.
Yes, sir.
What will happen when the ligands are at a farther distance? If the field is uniform, students, if the field is uniform, ligands are coming from, if the distribution of the field of the ligand is uniform, and there is a uniform field of the d orbitals of the metal ion, what will happen as they approach, as the fields are coming closer, students, there will be some rise in energy of the d orbitals. What I'm saying, how many d orbitals you are saying, students? Tell me. 5, 1, 2, 3, 4, 5d orbital. ठीक है?
Yes, sir.
They are degenerate, so I have shown them on the same line, same energy. They are the same energy. What will happen? What d orbitals you are aware? Can you tell me how many d orbitals? How you define d orbitals? What are those d orbitals, student? 5d orbitals. Can you tell me what are those? Okay. Think. What do you have? X. Supposing you have X, student, you have Y, you have Z. There are 3 X's we use. How many d
Yes,
orbitals
sir.
you say? DXY,
DXY, DYZ,
DXZ,
DXZ,
DX square
DX
minus Z,
square minus Y square,
and D.
DZ square.
All right, student. I thank you for helping me. I always take your help, students. You know why I take your help. Because I want you to understand everything. Now you will learn the things. You know, are the shapes, what type of shapes they have, students? Do you know the shapes of the d orbital, student? Did you see in the book? Shapes of 5d orbital, students. The when I say dxy, where is the electron density? The lobes which are shown by dxy. If this is my x plane, This is my y. This is my y student. If I say dxy, then what it shows dxy, where it is located. The dxy is always between dxy is always between x and y.
X
Tell
and
me
Y.
yes or no.
Yes, sir.
If I say dyz, it is between y and z axis.
Y and Z.
Dx is between x and z
X and
axis.
Z.
And dx square and y square, when I say dx square and y square student, what where they are? They are located
On the axis. They will be on the
on the
axis.
axis. You draw like this,
Yes, sir.
dx square minus y square. And when you draw dz square, that you know how we draw dz square. If
Yes,
this
sir.
if you are saying this is my z, then how you draw
On
dz?
the axis and then on the back we show.
You show some.
Yes, sir.
So the shapes of d orbitals, the probability distribution of electron is different. They have a direction student, as you can see. Out of the three are located inside the xyz axis, and the two are xy plane, xy axis and z axis, right? Okay.
Yes, sir.
All right, let me show you now something. Whatever we were trying, now we are showing it here. I mean, you have answered the question. I thank you for that. So students, here is a picture of the 5D orbitals. Yeah, see this x and y, dxy orbitals. This is our dz square, dz. These two sets. This is dx square minus y square. This is my dz square, and this is between x and y plane, x and y. This is my dxy, and this is x and z, dxz, and this is between y and z, dyz. ठीक है?
Yes, sir.
5D orbitals. Now students, these are the 5D orbitals. Where they are present? Sorry, where they are present 5D orbital? Inside the metal ion.
Yes, sir.
They are degenerate. They have a field. This field is symmetric.
Yes, sir.
Field of 5D orbitals. This is symmetric student. Now when the metal ligands start approaching it, what will happen? Ligands start coming near it. Now the question is, from which direction the ligands are coming? And you are, first of all, if I take the octahedral case, you know, you are aware of what is the shape of octahedral, student. What is the shape of octahedral? You are saying you are aware if this is our metal, student. How you are drawing octahedral? The ligands are here, 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 here. ठीक है?
Yes, sir.
I am not showing now any bond in this, because here is electrostatic model. These are point charges. These are point charges. I am not saying E bond formation. These are point charges. But I am saying the ligands are approaching. In the case of octahedral, you know what is the shape of the octahedral. You know what is this? If I say these are the three axes, students. What are these axes? They are at 90 degree.
Yes, sir.
90 degree. If one is x, other is y, then this is a z direction. Tell me, looks like that or not?
Yes, sir.
Three axes we defined, x, y, z. This angle is how much? 90 degree. This is 90
90.
degree. All are 90 degree.
Yes, sir.
Yes?
Yes, sir.
Okay. The ligands are coming from x axis, from y axis, to from the z axis direction, students, in the octahedral case. ठीक है?
Yes, sir.
To make the things more clear to us, we say, okay, we will draw a cube, student, because three-dimensional things, we have to make a picture of everything. I am not that good, but I am trying, student. Okay, this is a cube.
Yes, sir.
This is a cube. So, students, what I am saying, for example, student, if I say the metal is here, then what is happening, student? Thi- This is my one axis, another axis. These are the three axes, ठीक है?
Yes, sir.
And if I say this is my x, this is my y, this is my z, ठीक है?
Yes, sir.
The ligands are coming from this, from this, from this. ठीक है?
Yes,
Similarly,
sir.
there will be six ligands now here on the back. So these ligands are coming in the case of octahedral. When they will come near, as they are approaching near, student, as these ligands are approaching near, student, these are the ligands, as they are coming near and near. There is symmetric, there are 5D orbitals here. These ones, 5D orbitals here. The three are located in the three cases, the electron density is more in between the axis. And the two cases, the electron density is more along the axis. Which one? This dx square minus y square and dz square. So what will happen, students? First, the energy of these 5D orbitals, 1, 2, 3, 4, 5. Okay?
Yes, sir.
They are degenerate. Which one you are saying you have dxy,
dxy
dxz,
dy
dyz, dx square
x
minus
square
y
minus
square
y square
dx.
dz square.
What will happen? First, their energy will rise. One,
Okay.
2, 3, 4, 5. As they are negative, as there is a uniform distribution of field around them, electric field, another electric field is coming. There too, the energy will rise. The 5D orbitals, 1, 2, 3, 4, 5. And as the ligands approach in the case of octahedral, students, these two set of orbitals are more directed towards the ligands. Ligands are coming from x, y, and z axis in the case of octahedral. So these will interact stronger with the negative
Oh,
negative charge, because inside the d orbital you have electrons. Electrons negative charge, ligands negative charge. What will happen? There will be repulsion, students. ठीक है? And the which will experience more repulsion, student, out of these 5D orbitals. These two will experience more repulsion. Which one?
okay.
The dx square minus y square and dz square. They are going to be having more electric field as compared to the third one. Three orbitals. The three orbitals are located in which direction? Their direction is not towards the ligand direction. So ligand interaction with them is less. Ligand interaction with them is less, students. What will happen then? This will cause what we call as a crystal field splitting, student. There will be splitting of the d orbital, student.
Okay.
The d orbitals, 5D orbitals, student, their degeneracy is destroyed. They will split up because now it becomes asymmetric, student. The distribution of charge is not symmetric, is not same for all the 5D orbitals, but the distribution of charge is asymmetric, student. This was symmetric. This was symmetric field, symmetric distribution of field. Now the field has become asymmetric, and the result of that will be what, students? That there will be the three orbital, students, they will go to lower energy. They are not interacting with the coming ligands, but the two which are strongly interacting with the ligands, they are directed toward the ligand. What will happen, student? Their energy will rise. Their energy will rise. So here you will have two orbitals and three orbitals. So what does happen? The d orbitals get split up. Students get split up in set of two orbitals. Get split up in set of two orbitals. Student, as you can see, this is a triplet. This
Yes, sir.
is called T2G. Triplet. T stands for triplet. T2G. This is called T2G, and this is called EG,
EG.
student. EG orbitals. So there is a splitting of the d orbitals in octahedral crystal field. What I told student here is octahedral splitting of d orbital in octahedral crystal field. It is a crystal, it is a field. So octahedral crystal field. Octahedral crystal field. As you can see, this is a three-dimensional picture. This is the metal. Can we see the metal, student here? This is our metal. If I supposing this is my metal, and this is a cube has been drawn to the scale. The ligands are coming where? See, in the case of octahedral, they will coming towards from the axis. These are the three axes. This is my x-axis. This is my y-axis. This is my z-axis. Okay? So ligands are coming from x-axis. Ligands are coming from z-axis. Ligands are coming from y-axis. How many? One, two, three, four, five, six. Okay?
Yes, sir.
So six ligands are coming. This is the octahedral shape as you can see. If I draw this,
Yes, sir.
I can see an octahedral, student geometry. So the result of this is that the d orbital has got split up. First the energy is raised, student. Then they get split up into two set of orbitals. One is the triplet, other is the doublet. So that is doublet is called EG and other is called T2G orbitals. So this is called crystal field splitting. What we saying? What is this known as, student? Crystal field. So the average energy of the d orbital in spherical crystal field. This is the average energy, and this is the free metal, student, free metal ion. So we say the free metal ion in the gaseous state, the energy first rises and then there is a splitting of the energy into two set of orbitals T2G, and this is called crystal field
Crystal
splitting
field splitting.
energy. Delta O stands for octahedral. In the case of
Okay.
octahedral, we are saying this is the crystal field splitting energy. Crystal field splitting energy. Crystal field splitting energy, CC, is delta zero. Delta zero is the crystal field splitting energy. Any doubt up to now? Tell me.
No, sir.
Okay. Here is a clear picture of what we said, students. This picture is given in the book. This picture has been taken from the NCRT book. However, we can't draw to the scale all these things. Now here everything is more clear. Let us see what we are trying to say, students. So here what we are trying to show, student, they will ask you what is.
Sir, is it asked to draw this
No,
diagram
no,
in the
no, nobody
exam?
is asking you to draw the. You will draw the way I have drawn. That's all.
Okay. Okay.
If required, we will show when we will take questions. Everything will become clear. You know that we are used to solving a lot of questions. Crystal field splitting. The question has been asked, student, what is crystal field splitting? The question in the paper. What is your answer? What is crystal field splitting, student? What is crystal field splitting? We have already told when the ligands approach the central metal ion, if it is octahedral, then there is a splitting of the d orbitals. 5d orbitals get split in two sets. Why? Because the three orbitals of the d are located, their lobes are inside the x and y axis, so they are not interacting with the ligands, but the one two set of orbitals, which one? Dx square minus y square and dz square. They are strongly interacting with the field of the ligands, hence their energy is raised and the energy of the T2G drops, and therefore there is a splitting of the d orbitals. Now the interesting thing, student, this what we call this, as you can see, this is called a barycenter, which is, I say, is a 0 point, supposing 0 point, student. Here, these d orbitals, their energy, these are my x, y, and z axis. This is my metal ion, student. Inside the metal ion, how many orbitals you are saying? 5d orbitals. And the shapes we have already shown you for reasons, because we wanted to show you why the splitting takes place. Because the interaction is different, student. Repulsive forces which are operating in the field experienced by two set of d orbitals and the other three set of d orbitals is not the same. Therefore, they can see that they get split up. So what happens, student, if this is my, what they say, barycenter or 0 point, student, here this is my, student, delta zero. This is what is called, this is the crystal field splitting energy. So delta zero is my crystal field splitting energy. If I consider this, what happens? This, the two orbitals are raised, their energy is less. And these are coming down, students. What happens, student? As you can see, this is my point, student, here. Okay?
Yes,
So
sir.
here and here we have shown 2 points, student. They experimentally they found that this value comes to be 2 by 5 delta 0.
Okay.
Actually this is minus because the energy drops here, minus energy. So this is negative, student, here, minus 2 by 5 delta 0. Minus 2 by 5 delta 0. What is that equal to? Minus 0.40 delta 0. Okay?
Yes, sir.
And on the top, these are the three orbitals. On the top you are having three. The total value has to be 0 if I will add the two, student. That is the my barycenter or the 0 point. Now this value is then 3 by 5 delta 0, students, plus 3 by 5 delta 0, which will come to be, students, how much? 0.60. 0.60. ठीक है?
Yes, sir.
The result of this is, student, what is it? 3 by 5 delta 0 plus 2 by 5 delta 0. Total, what is this value? Delta 0.
Delta zero.
5 by 5 delta 0. That is what we are saying, crystal field splitting energy. This is our crystal field splitting energy is delta 0. Total value is delta 0. So the total value is delta 0, students, and this value is the center where we are saying where this splitting has taken place. Now, the important point to note is that we are using now field of the ligand, students. Certain ligands have more field and certain ligands have less field now. Now the question is coming, the what is the field strength of the ligands? Because now we are talking about field, student. Field strength of the ligands. What we are saying, certain ligands have stronger field and certain ligands have less field. So the ligands which have stronger field, the value of delta 0 will be more. The
Yes, sir.
splitting will be more, students, for a strong field, and the splitting energy will be less for a weak field.
Weak field.
In other words, what you are saying, students, now these are my 1, 2, 3, 4, 5 How they are splitting? For octahedral, this is a case of, what is this? I'm talking of
Octahedral.
octahedral. In the case of octahedral, these were five which were degenerate student. These are five d orbital, 1, 2, 3, 4, 5. They are degenerate. And what happened, students? You are saying there is a splitting, just to show you. ठीक है? This your call is T2G, and this is
Yes, sir.
your
EG.
E-
EG.
EG. This is my delta zero, octahedral splitting, crystal field splitting. And if you have student a weak field, then what will happen, student? This energy gap will become less.
Okay.
This is my delta zero. ठीक है? This is your T2G. This is my EG. This is a strong field,
Yes, sir.
and this is a
Weak field.
weak field. How do I know? This delta zero of strong field is more than delta zero of weak field.
Less field.
ठीक
Okay.
है?
Yes, sir.
Therefore, we must know which are strong ligands and which are weak ligands. As I said in science students, how can I say it is a strong or weak? I have to have
Experimental.
experimental evidence.
Yes, sir.
So they have experimental results, student. After that, they give a list. They have arranged them in some order. So, student, experimentally the strength of the fields have been determined, and in the book they have given this series. These are halogens are coming lower, student. Halogens are coming lower, and OH minus. But the carbon, carbon CN, EN, carbon and nitrogen, you can see carbon monoxide is on the top. That means it has a very high field. When carbon monoxide will be there, student, the splitting energy will be very high. Crystal field splitting will be very
Yes, sir.
large. So there will
Yes,
be
sir.
large crystal field splitting when strong ligands are there. So this is also called spectrochemical series because they determine this by spectroscopic methods.
Okay.
Spectrochemical series, students. This is given in the book. Like after experiment, they say this is a series. So CO is strong ligand. Which one is this? Cyanide.
Cyanide.
This is EN is which one? Ethylene diamine.
Ethylene diamine.
Ammonia is a strong.
Ammonia.
EDTA is a strong.
Yes, sir.
Ethylene diamine tetraacetate.
Yes, sir.
And up to this, water is even coming in the strong list, and then it is decreasing. And not like in between they are coming. The question was asked, what is a spectrochemical series? What is your answer, student? What is a spectrochemical series, students? Everything is a question for the paper. What is a electrochemical series, student? What answer you are giving? What is a spectrochemical series, students? If you arrange the different ligands in the order of their field strength, increasing order, that is called the spectrochemical series. Okay? That is what we have shown you.
Okay.
So we have arranged them in increasing field strength. How do we know? From spectroscopic data, they are arranged in this order. All right. Any doubt up to now?
No, sir.
Okay, student. Now, what is the consequence of this, student? Is a very important point here, student. What will be the result of this? The energy gap between EG and 2G is called crystal field splitting energy. They asked the question in the paper. What is a crystal field splitting energy? Many times they have asked in the paper. What is your answer? Tell me just 130 seconds. Tell me the answer, student, fast. What is crystal field splitting energy? Which we are for octahedral, we are representing it by delta zero, delta O. O means octahedral.
Yes, sir.
What is crystal field splitting energy, student? The energy gap between.
The energy gap between the T2G and EG.
Okay. You don't have to write more. Actually, we have to be accurate. I said precise words. Now, students know it, but they are not able to write in the paper. See, the trouble is that. Oh, I try to make it very sure that you understand. This is called delta O zero. Sometimes you will see this is also written as delta DQ. That is called delta dq is actually used term from quantum mechanics from the wave equations. We are going to use delta zero in the book. They have not mentioned in the NCRT book this
Okay.
dq. So therefore we are not taking dq means daisy quantum. So it is a unit of energy, a representation of energy otherwise. Actually, the value is written 10 DQ. Those students who are going for G and other competitions. So we just shown you that value also. So because these are the D orbitals. For D orbitals, you know what is the value of L. Uh, S, P, D, L will be 0, 1, 2. L is 2. So that is based on spectrochemical and wave functions of quantum mechanics basically. So dash Q is a representation of energy. So what is happened, student? Delta, we will be using delta zero in all our calculations also. Okay? The overall energy, because the overall energy is maintained, the energy of 322G are lower, are lowered or stabilized by zero point 0.4, and delta zero energy of the 2 EG are raised by zero point 0.6 students. Zero point 0.6. The overall
Okay.
energy is conserved, student. That is what he is trying to say. What has happened? What has happened? What he is trying to say that there are two here and there are three here. Okay?
Yes, sir.
Now, if the splitting is taking place, this involves stabilization. Lowering of energy means stabilization. In chemistry, all the time we are saying lowering of energy. Lowering, how much is this? Is 2 by 5? 2 by 5 student. And this is then minus. Lowering means less energy. And this is 3 by 5 plus. Plus. Okay?
Yes, sir.
Now, what we are saying, this point we are saying, what we have said in the book, he says bay point or 0 point. So overall energy is maintained. The energy of 3 T2 are lowered or stabilized by 0.40. Delta energy of 2 EJO are raised by 0.60. Why did I show? How much is this coming? 0.60.
0.60
How much it is going? Minus 0.40.
minus
And let
0.40.
me see what I am trying to say, the energy conservation, because this is the 0 point. Okay?
Yes, sir.
This has gone up, this has gone lower. This stabilization, this is stabilized, and this is a destabilization.
Yes, sir.
Destabilization. Wherever energy goes up, destabilization. Where energy goes down, stabilization. And let me see what is the total value of the energy. There are two of this. 2 into plus 3 by 5. How much is that? Plus 6 by 5. And this is how many? 3 into minus 2 by 5. How much will be that? Minus 6 by 5.
Minus 6 by 5.
So if I add the two, the energy is conserved. आ गया zero.
Yes, sir.
Net change is zero. This point, which I am calling as a bay point, student zero. Clear?
Yes, sir.
And nobody will tell you these things what I am telling you, because students will never understand unless who will explain to them, very difficult, because who will tell them, it's not, nobody is interested to go into that details. So it is clear.
Okay.
Therefore, students, what you find that the lowering of energy is taking place from this waypoint or 0 point, but overall energy is conserved. As you can see, students, uh, the total energy is not changing. So another important point we want to tell you, student, as you can see, for titanium S2O, Ti3 has D1 configuration with the electron occupying the crystal field stabilization. Here, if I have two types of field, we have said is strong field and weak field. There can be a strong field, and when strong field will come, the energy gap is more. You can see this energy gap is more. Tell me, this is delta zero is more here as compared
Yes,
to
sir.
here.
Yes, sir. Yes, sir.
So this is a weak field, this is a strong field. Student, strong field will have a bigger gap. So if in the case of TiH2O6 3 plus, tell me how many electrons are there in titanium 3 plus? Fast. 30 seconds are given for everything.
Titanium 3 plus will be
What is the D count? Scandium, titanium, what is the problem? First I write
uh,
scandium, then I write
D
titanium.
will be 0. 1. 1 electron.
How you start? 21, 22 atomic
22.
number. So what is titanium in the ground state? You are saying it is, what do you write? Argon.
4s2 3d2.
So writing 3d2 4s2.
4s2 and then
So
3d1. 3 plus.
what we are saying 3 plus. So titanium 3 plus
3d1.
is 3d1 count. Okay? One
Yes,
electron
sir.
in the D. I have shown it, one electron in the D. One electron in the D. And this is stabilization because there is no electron in the, there is no electron present in the strong field. So if I say what is the crystal field stabilization energy, what is the crystal field stabilization energy, students? In this case, you are having minus 2 by 5, and how many electrons are there? One electron
1.
into n number of electrons. So what will be that? Minus 2 by 5 into minus 2 by 5 delta 0 into number of electrons. 1. So what we are writing? Minus 0.40 delta 0. Minus 40 delta 0 is the crystal field stabilization energy of this compound, this complex, titanium S2O3 plus.
Yes, sir.
Therefore, this compound will be unpaired. It has one unpaired electron. And how will I write, student? T2G1 EG0. This is the electron
Okay.
configuration of this complex. Clear?
Yes, sir.
If there are two electrons, there is no problem. Then I will multiply this by 2. That will be the crystal field stabilizing energy. Next electron is also going into the, if I take D2, if I have a D2 student, then what is the problem? What will be the, then it will be T2G, okay?
Yes, sir.
And T2G2 EG0. And
EG0.
the crystal field stabilization energy will be equal to 2 electrons into minus zero point 0.4 delta 0. How much? Minus 0.80 delta 0. Clear?
Yes, sir.
Up to 3 electron, no problem, student. Now for weak field, you see the energy gap is less, energy gap is less. But supposing now instead of 3, I have 4 electrons. The problem comes supposing if I have, student, now let me give you example. Now I am saying when electron becomes more than 3, D4, D5, D6, D7 and like that. Now the 3 electrons go here, but what will happen to the 4th electron? The 4th can go here or they can pair up. Two possibilities. ठीक है?
Okay.
And now the Now the story is, student, if I have D4, D5, D6, and there are two possibilities. I'm saying D4, D5, D6. There are two possibilities, students. Either the electron pair up or electron go here. It will depend on, this is my strong field and this is my weak field. ठीक है?
Yes,
If the
sir.
electron pair up, there is another energy which is called pairing energy, student. Pairing energy. I am representing that by P, student. Energy will be required to pair the electron. Energy will be required to pair the electron because electron repulsion pairing. And if now the question is, if the crystal field splitting is more, if the crystal field splitting is larger, student, the pairing energy is less. If delta, this is my crystal field splitting energy for octahedral is more than P, student, what will happen? In such case, where this splitting energy is more delta O0 and there is a pairing energy. Okay? Two things are involved now. If delta O0 is more than pairing energy, then what will happen, student? Pairing will take place. What will be happening? Pairing will occur.
Pairing will take place.
Therefore, in the strong field, if I have a D4 count, what has happened, student? There is no electron in the EG. The configuration is T2G 4EGZ for strong field. Strong
Yes.
field is this case 1. ठीक है? When
Okay.
delta 0 is greater than pairing energy. What is pairing energy, student? The energy which is required to pair the electrons. ठीक है?
Yes, sir.
And second case 2, if if pairing energy, if second case I am saying, student, if delta O is less than pairing energy, delta octahedral splitting energy is less than pairing energy, then what will happen? This is a case of weak field
Yes, sir.
ligand, and that was a case of
Strong field again.
strong field ligand, students. Strong field ligand. So if delta 0 is less than P, then what will happen? Pairing energy is more, then the electron will go to the EG orbital. Then what happens? Then pairing is not taking place because pairing energy is more than the crystal field splitting energy. So in this case, what happened? You can say the D4 will be configuration will be T2G3
EG1.
EG1. So this becomes, student, low spin complex and this becomes high spin. There are more unpaired electrons. Here, how many? 4 unpaired electrons.
Yes, sir.
And in the first case, students, 2, how many unpaired electrons? In that T24, T2G4, as you can see, 2 unpaired electrons.
Two unpaired electrons.
Unpaired electrons. So students, we are actually involved in two things now. One is the crystal field splitting energy. Second is the pairing energy. And on that basis, we will be writing students the electron configurations after the splitting of the d orbitals. So we have defined to you two fields, student, strong field ligands and weak field ligands. And on that basis, we will be able to, students, write these electron configurations. I hope everything is clear to you. Do you have any doubt? So you will have low spin complexes and high spin complexes. Clear?
Yes, sir.
So this is the first part of the crystal field splitting energy. I have tried to give you a lot of information which is not available in the books. So we will continue and meet in your next class. Every class will be important and you will be able to understand and answer all the questions in the different papers which you are appearing. Okay.
Okay, sir.
Okay. Good night. Then we will meet you in the next class.
Okay, thank you, sir.
All right.